Okay, question 2. So this is an overlap question from the foundation paper, and it's about waves. So we can see we've got a wave diagram here, and it says calculate the wavelength of the wave. So what makes this tricky is if that's the rest position there, usually we'd go from, say, the peak of the wave to the peak of the wave, or the trough to the trough, but we haven't got that. We've only got half a wave on the screen. So we're going to go from midpoint to this midpoint here. In reality, we'd go over to there because we want one full wavelength. So we can imagine if we're going up on the wave here, we'd go to the next place where we're going up on the wave. We don't have that, so we've only got half of a wave. But we can see that with that half of the wave, that's 14 centimeters. And then I just need 2 lots of that. So half of the wavelength is 14 centimeters. Let me rub-a-dub that. So I need 2 lots of that 14. The wavelength is 28 centimeters. Tricky question. Nice one though. Next one, I've got a student on the shore and they're watching ripples on the surface as they pass a toy boat. So when these ripples pass, that boat will bob up and down. And we've learned that frequency equals the waves divided by the time, or bobs over time. So it says the student's got a stopwatch. Brilliant. They're going to need that. Describe how they could determine the frequency. So, well, given we know that it's the waves over time, we're just going to pick a spot. Makes sense to use the boat. Set a time. Let's set that to 60 seconds. We're then going to count the waves as they pass. 1, 2, 3, 4. And then we know it's just the number of waves divided by the time. And then to put that all into words. So frequency is the number of waves each second. Pick a point on the surface. We're going to pick where the boat is. Time for 60 seconds using a stop clock, and then the last bit for the mark. Count the number of waves that pass that point, and frequency is the number of waves divided by the time. Okay, so that's that question done. Next one, we've got foxes stab wolves kicking in here. Remember, that can also be written as F, and they'll use velocity instead of speed, and they'll use that for wavelength, the lambda sign. They're both the same, they're equal to each other. And it says calculate the wavelength. So we want to calculate this or this. I'm going to use this one because this is the one we use most. So we know W equals S over F. Let's check the speed. No unit change there. That's perfect. No unit change there. So we're just got to plug those numbers in. So W equals S over F. 1.5 divided by 0.7 equals 2.1 meters. And then the next part is we've got transverse waves. Describe the difference between transverse and longitudinal waves. So we know if we've got 2 waves, so let's do transverse there, longitudinal here. We're going to have a vibration or an oscillation. And that's going to send energy. So there's energy going along in both. In this one, the vibration is at right angles to it for transverse. And in longitudinal waves, it's parallel. And we know that this would be water and light waves. This would be sound and P waves for earthquakes or seismic waves. So we've just got to put that into words, and it is that stick with V, P, D, O, E, T. There you go. So in a transverse wave, the vibration is perpendicular to the direction of energy transfer. There's a mark, and then we just got to change the word perpendicular to parallel for the longitudinal. So in longitudinal, the vibration is parallel to the direction of energy transfer. That's your model answers. That's that question done. Nice short one.